Hi everyone, my name is Alexandra Krupko. I'm Employer Brand Specialist at Intellias. Glad you've joined us this evening and hope the information Hannah will share with us will be useful for everyone. And while the rest of our participants are joining in, let's talk about Intellias a little bit. Intellias is a technology enabler for the world's biggest companies, exciting projects, international clients, global representation, 8 development centers, and more than 300 open vacancies. That's what Intellias is about. And we create really unique software solutions for more than 2 billion people worldwide with the help of 3,000 experienced specialists. And no matter how fast we grow, we always adhere to people-first approach. I invite you to visit our site with vacancies, and who knows, maybe a career match will happen. I'll share the link in our chat. And now a couple of technical issues. You can write your questions to the chat during the presentation, and Anna will answer them. After the presentation, I guess we'll also have some time for Q&A session. Also, please mind that there will be 1 minute delay due to YouTube streaming rules. That's all. We also be grateful for your feedback. I'll leave the link to the feedback form in the chat. Please share your mind with us. So that's all. Let's get started. I'd like to introduce our speaker, Hanna Kaplun, Principal Test Engineering Lead at Intellias. Anna, glad to see you, and the word is yours.
Hello, everyone. I hope that this evening will be a pleasure to all of us. We'll talk about test design today, and I hope it's useful to get to know a little bit better if you're not familiar with the more complicated test design techniques. And for those who are familiar, maybe you will find something new about how to implement it in your projects, how to automate test design process where it is applicable and possible for your solutions. So we talk about test design today, and our topic is about decision trees and state transition. I hope you see my screen now. Is it visible?
I guess so.
Oh, okay, so you can see it, good. So decision trees and state transition, something more complicated than equivalence partitioning and boundary value analysis. We will talk about the test design techniques which are based on trees today as the data structure. And we will consider a few examples in the end of this presentation. Hopefully you will find them useful, and I will do my best to make it as interactive as possible, which makes it makes a little bit difficult to use YouTube with the delay about 1 minute, but I hope we will make it happen anyways. Please be sure to ask your questions. I will see them in my chat and will do my best to answer as soon as I see your questions. Don't wait up till the end of the presentation. We will do it on the fly. So as soon as you want to ask something, please shoot. Note that there is a slight delay. As soon as I get your question, I will answer it. So let's proceed with decision trees and state transition. Graph-based test design, what's it all about? We will, so not very interesting slide. I think we share the presentation afterwards, so hopefully you will have a look at the links that are presented here. And this slide about myself, I have lots of different experience in testing with different domains. I have passed a few certifications successfully. I work in automotive industry at the moment, and I do some speaking, writing in the testing domain as well. So you can read up later if you are interested in that slide. What's more important is what we are talking about today. First of all, the idea of these techniques. So we are speaking about state transition and decision trees. We can also compare these techniques to cause effect, and we will see the difference between decision trees and cause effect, if any. And we will talk about the applications, of course. So the idea is to make sure you can distinguish between the cases where each of the techniques is necessary. So where you need to apply state transition, where you need to go with the decision tree, or maybe you're fine to use cause-effect diagram. Note that these are complex test design techniques, complex meaning that they are not complicated. They may or may not be, but they combine different parameters. Note also that not all of them are data-based. State transition is a behavior-based test design technique, meaning that it will not be the case of the same scenario with different data points, data entries somewhere on some of the steps and different expected results afterwards. They are quite different, but some of them work with data, some of them work with behaviors. Anyways, all of them may be applicable in the definite cases. So we will talk about the applications second. We will define how to code the test design. Note that it is not about system level testing. So I am not talking here about test automation in terms of imitating user actions, writing it down in some source code and then running it on a regular basis or whenever you want. How to code it part refers to how to automate test design and what you need to do it. So the process of automation of test creation, that's the idea. We'll see how it goes, what we can apply, what are the constraints, what possible benefits maybe are, where you can do it, where it is not worth it. It may be the case, of course. And finally, we will consider a few examples. We will consider a few trees, as this is the graph-based test design techniques. And we will have a look at the possible implications, namely the number of tests you might encounter when applying these test design techniques and the difficulties in implementing those tests and maybe executing them. So sometimes, as we will see further, executing the test cases might be a more complicated task than the test design itself. Not always the case, of course, but still it might be a challenge. We'll see the example of that. So let's proceed. State transitions, decisions, and cause effect. Where goes what? First of all, let's consider decision trees and state transitions. Yeah, what's the difference between the two when we apply each and how we distinguish between them? Decision trees and state transitions require you, as in any test design technique, to have a look at your requirements. As soon as you have a look at your requirements, you can decide which technique you need. It is true about any of them, no matter which decision table, state transition, whatever. You always look at your requirements and make some decision, come to some conclusion on which test design techniques will work for you best in this exact case. So what your requirements look like if you want to apply a decision tree. Your requirements are a tree. What does it mean? It means that it is some kind of a diagram where there are some conditions and the tree is kind of growing from top to bottom, as they always do in maths. So there is some starting point, then there are some points of making a choice, and the actions that follow each choice. The choices can be interconnected, the choices can be based on different parameters, different sets of parameters maybe, and in each choice, you want to apply some sequence of actions. So in this case, your requirements might essentially look like a tree. It can be graphical, yeah, it can be a scheme, the drawing of a tree. If your requirements are semi-formal, you might see that it is the if-then statements. So if you use something like Gherkin or some other formalized way of writing requirements, if you see the nested if-then statements, or if you see a few parameters going into a decision, into the if part, working together, then you might want to go with a decision tree. And there are some dependent conditions. Dependent conditions mean that the result of one condition causes another condition to follow. So you have the initial condition and you have options A and B as a result. And depending on if it is A or B, your application proceeds one of the ways. So the flow cannot make one decision in a row. So one decision that defines all the further steps. It is not that way. If you want to use a decision tree, it means that there are some chains of decisions. One decision causes another decision, then it causes another decision, and so on. And depending on the previous results, the new steps are made. That's the idea of a decision tree. In this case, it is typical to use graph to visualize that. And if you see that this is the case, you are very likely to need a decision tree as a test design technique. What's the difference with the state transition? Obviously, you need state transition if you have states and transitions, but it might not be that explicit. Of course, you might have a nice state transition diagram in your requirements as well. The difference between the decision trees and state transition diagrams is that decision tree is a particular case of a state transition diagram. So state transition diagram can be in fact an ad. It is not often a tree. It can contain loops. It is any graph. It is anything that looks like a graph and displays the transitions between some states in your program. What is not always so obvious is using state transitions for simultaneous actions on one entity. So your entities often go from one state to the other. And okay, you can use state transition diagram for that and perform some positive tests. Good, well, nice. But simultaneous actions is something to think about, because this might result in some issues, and you might want to perform the negative tests based on state transition diagrams. We will see how it goes a little bit further in the presentation. Simultaneous actions, it is not only about performance. So when you plan your testing, you might want first to apply functional testing regarding simultaneous actions, and only then proceed to performance. Of course, unless you encounter some issues during this functional test. As soon as you are ready, you can proceed with planning performance testing, performance profiles, or what your users do, what the load is, and so forth. But before that, you need to make sure that your program works well enough with simultaneous actions without lots of load. So without further ado, you test a few users doing something together on one entity and seeing how it goes. These tests can be planned. We'll see how. If you have forms with different parameters allowing choice and various ways of input causing different results, you might also want to consider it as a state transition case. Maybe you will want cause effects here, maybe you will want a decision tree here, but note that the forms with lots of different entities that have states like checkboxes, radio buttons, you might want to think about it as state transitions. Note also that the input fields, or actually any UI elements, can be considered not only as the way to input some data, but also as the entities having states. And based on that, you can create additional tests that might cause something different, different kinds of issues than those that you encounter based on data. So you can use your tests and build them on data. So for each checkbox or radio button, you can set a Boolean variable, for example, to consider it true or false, checked or unchecked, selected or unselected. Or you can also consider it an entity with a state that can be either selected or deselected, and you can go from selected to deselected and back, and consider this from state transitions perspective, which might bring you a different set of issues. A quick example here is that for an input field, you can consider different ways to provide your input. So the input you provide, these are the tests that are based on your data, while the way you provide this input, these are the tests based on state transition. Your input field has two states, empty and filled in. Something is put there. And you can go again from the first to the second and back. So you can empty it, or you can fill it with something, but you can fill it in different ways. You can use your keyboard. You can copy and paste something. You can copy and paste using the hotkeys, or you can use the drop-down menu, or maybe you can drag and drop something, select, highlight something on your web page, and then drag and drop. And in this way, you might encounter more issues, something like, okay, when I use my keyboard, I cannot input invalid characters, but when I copy and paste or when I drag and drop, then I can input invalid characters in a field that allows me to do so. So state transition perspective might bring you something more than just purely data-based tests. Or you might consider it as part of your state of your database tests, and, for example, include it as the parameter into your combinatorial testing, and then it'll become a part of a bigger database model for your tests. Also, obvious application is the UI wizard, so something where you define some settings and you use steps here and back. It is definitely state transition, so you can change the sets of data and you can step between the screens. This is quite obvious application of the technique. Therefore, these are the typical cases of decision trees versus state transition. Hope it makes some sense. If you have any questions, please write them on the chat. I will go forward, and if necessary, I will come back. If you have any questions, please write them, and I will get back to this slide and explain more. Decisions and cause effect. That's a trickier thing. Decision trees, decision tables, and cause effects are very similar. The difference is in dependencies and lack thereof. So if you are using decision tree, it is the case of dependent conditions. If you're using cause effect, all your parameters may have some complicated conditional logic. So you have a huge set of parameters and they all define some output. it. But the key difference is that decision tree has nested conditions, while cause-effect can define the result at once from the predefined set of parameters. Yeah, that's the key idea. From source code perspective, you can define both as nested conditions, but in the first case, in case of a decision tree, the conditions are dependent. The result of the first one determines which is used next. In cause-effect, you have a set of parameters, and all of them, these set of parameters are somehow evaluated, interconnected, and or not, sorry, whatever, but the whole set and their logical conditions, the ones that unite them, determine the outcome. That's it. So this is the key difference. If you have the case of a cause effect, of course, you still can use the decision tree for that. It's not an issue, but note that you cannot use cause effect instead of a decision tree if your conditions are dependent. Okay, so to generalize it, to sum it up, decision trees are a particular case of a state transition diagram. We can make it so if we consider decision tree a graph and state transition is based on graphs. So we can somehow say that the decision tree is some particular case of state transition. We can consider cause effect, yeah, a particular case of a decision tree. So we can make it happen. Yeah, we can use the techniques interchangeably if we consider the cause effect also to be a set of conditions. However, they are applied at the same time, kind of. So they do not depend on each other. They are independent. They can be applied in parallel. You can also think about it as synchronous and asynchronous decision making. If you can make it synchronous, then it's cause effect. If you can't, it's decision tree. Okay, that's the general gist of it. I suppose your requirements will kind of the same in both cases, but I wanted to highlight this key difference, which you might notice if you have a closer look at your requirements. So in order to decide which test design technique is yours, you need to think carefully if the conditions are dependent or not. Okay, that's the way to go. Okay, are there any questions there for me to answer, or we can proceed?
Oh, we don't have any questions yet.
Okay, I hope that was more or less easy part, so let's get a little bit deeper into decision trees. So decision making, yeah, how we do it and where do we apply it, how we maybe make it graphical. The idea of a decision-making process is that we have someone who makes the decisions or something that makes the decisions, and it gets the internal knowledge and external knowledge as an input. It produces some action. The action changes the conditions somehow, and these results may change this internal knowledge and external knowledge, and the process repeats. You can think about it as reinforcement learning. So if you're familiar with some machine learning techniques and kind of machine learning ideas, approaches, then you can think about decision making as reinforcement learning. So your decision maker learns from the reaction of the environment. There are some intrinsic character knowledges, yes, skills and so forth. And there is the knowledge of the external environment. The more this decision maker learns about the environment, the better decisions they make. That's the idea. but the environment is out of our control. So we may increase our knowledge about the environment, but the environment can change, and we cannot always predict how. If we could, we would go with cause effect, but we can't, and that's why we go with decision trees. That's the idea of decision making. The obvious idea of applying this is a game tree. If you have ever tested some game dev, some quests and so forth, you might have created decision trees based on the game logic. It looks like this graph on the right you see here. Note that the further conditions are based on the results of previous ones. So, is enemy visible? Yes or no? If no, we consider this new condition is enemy audible. If it is yes, we choose the different condition. That's the idea of a decision tree. Note that we cannot always evaluate all of the conditions at the same time. Okay, so we could evaluate all of the conditions you see on this tree at the same time. We could go with cause effect, but we might not be able to do that. And that is exactly the reason why we need the decision tree. So the decision in one bifurcation point results in the exact new decision you want to make. Okay? The conditions differ depending on the results of the previous ones. When you test based on a decision tree, you can see that the path you follow is highlighted. So in fact, the number of positive tests here is the number of paths through the decision tree. Is the number of leaves, yeah, in this case. And the negative tests are the number of missing leaves. You see, this is the example of a missing leaf. It might be a little bit more complicated than that. For example, if you have the same action applied as a result of a few conditions, it might be drawn as a net, but it is in fact a tree. So you will need to split it to make it a tree, and afterwards you can apply the same idea. So the number of positive tests is equal to the number of leaves. Essentially, it is the number of paths through the tree. Okay, does it make sense? I hope it does. Okay, let's go further. Could you please provide some practical examples? Yeah, of course I can. We'll get to that. It'll be the last part of our talk today. The decision trees, yeah, how we can use them and how we can use them, we'll get there, but they can be different and they can have some peculiarities you might want to keep in mind, okay? First of all, you might see the decision trees which are based on logical operators. Yeah, that's the classics, and, or, and you see these two trees which illustrate and condition and or condition. Okay, you can see that the leaves here are the same. This is exactly what I have talked about previously. So if the actions you want to make are the same, then if you want to follow all the trees, yeah, all the leaves, you will need to draw them on your tree as many times as you need to based on the decisions you make. Okay, so let's consider this example. A and B, and A can be yes or no, B can be yes or no. Yeah, two conditions, both are Boolean. And how is that an AND? Logical AND is true if both of the conditions are true. So you can see if A and B, then action 1. This is our path through the tree resulting in action 1. If A and B, then action 1, otherwise action 2. That's what A and B means. For this reason, if any of the conditions is no, then we go for action 2. This is how you can create and on a decision tree. And same for or. A or B, then action 1, otherwise action 2. Or condition is false only if both conditions are false. So A is false, B is false, then we do 2, otherwise we do 1. That's how we draw or on the decision tree. Okay, these are conditions, more or less simple, I hope. The second type risk consideration is branching, and there might be more than binary outcomes. You can see the 2 graphs here. Okay, 3 graphs here. Yeah, 3 graphs here. 2 of them are the same. Namely, they show the same action, and the same condition and the same action. These 2 are the same. You can see that here we have one condition with 4 possible outcomes and respectively 4 possible actions. Okay, and here you can kind of transform this to the binary tree. Why would you want the binary tree instead of this one? This seems simpler. Note, however, that binary trees are easier from a test generation perspective. And for this reason, you might want binary tree instead. So you might want to transform your tree with more than binary conditions first to binary, and only then proceed with calculating all the paths through it. Finally, the most complicated case, bad news, you can have randomness. Randomness is kind of always bad news. It makes your life harder. Here you see the example of a random tree where the condition is flip a coin. Flip a coin can result in either true or false. Okay, the probability is 1/2, yeah, 0.5, and it can result in the different action depending on the result of this condition. What's wrong with random conditions? It is not always 0.5, and you cannot predict exactly the time you will need to execute the test. Why so? It is random, so the worse, the lower probability you have, the more time you might spend trying to generate this result in order to perform this test case, to execute it. And that's the problem with random conditions. You might see it in some cases, however, especially if you test something black box and you cannot control the results. I will give an example a little bit further with the randomness. And you will see the case where you can meet it in the real world, also dealing with machine learning. But okay, let's proceed further, I suppose, and get to the more interesting part. Okay, that's about decision trees. Any questions so far?
No,
okay.
no.
Let's go for state transition, and maybe you might want to ask something else about these 2 techniques. So state transition. State transition can bring you a few different kinds of knowledge. First of all, you might want to consider it in the similar way to a decision tree. So in a decision tree, the number of tests is equal to the number of paths through a decision tree with the outcomes as leaves, and the number of tests is actually equal to the number of leaves. It can be considered the same in state transition if you have a graph with start and end point with the initial state and the destination state, and you can count all the kind of flows here, all the possible ways through the graph, and this can be considered a positive case, yeah, one single path through the graph is the positive case. And here you go, you count the whole set of paths. The number of them is equal to the number of your cases. That's more or less complicated case. So if you use state transition for end-to-end testing, that may be a good approach to follow. But you might want to use state transitions for simpler cases. You might want to consider the atomic transition as a positive case. That will give you the atomic coverage. I won't cover coverage here and all this stuff. So state transition is a topic in itself, I suppose. But there are two main ways to go for positive coverage. First is covering all the paths, and second is covering each transition separately, considering each transition a separate test case. When you have the states of an entity, you might go for the second approach. So the example here being you have something you can delete, and then you can undelete it, and you can archive it, block it, unarchive, unblock. Then you can delete the blocked or delete the archived, and so forth. The simplest way to think about it is your workflow in Jira, whatever backtracking system you use. You have the workflow, it's a state transition diagram. You can have a look at it, and then you can consider each transition from one state to the other as the single test to make. Okay, the interesting stuff there, however, is the tests that are not there. You have different ways to represent a graph. And for negative testing, you might want to go with the decision with the state transition table, the grid you see on top. State transition grid is the matrix where you have the equal number of columns and rows, and it is equal to the number of your states in the graph. The cells give you the positive transitions, so those which are there, okay, which are supposed to be there. You hope they are there. But it is simple, yeah? The interesting stuff goes where there are no transitions, or there shouldn't be. These are the cases you might want to perform to make sure that it is not possible to make your database inconsistent by pushing your entity into the state it is not supposed to be. The idea of these cells where you see no, the empty cells, the cells where there should be no transition, are the ideas for negative testing, including the simultaneous actions on the entity. It's something like try to delete what is already deleted. How you go for it? You open, if you have web application, it's very simple. Yeah, you open your entity in two separate tabs or in two separate browsers if your application doesn't allow that, or in two separate devices if it's that bad. And you delete it on the first device, tab, browser, and without refreshing the page, try to repeat the action in the second tab, device, browser. That's the simplistic example, but I hope you get the idea. The nice thing about this view is that you can create and count the number of not only positive tests, which is quite a simple task, but also the negative tests. The harder is to make them happen. So as soon as you count them, you can then think very carefully about each case and find out if it is possible to make it happen in your application or not. So as soon as you define this test, that's the easiest stuff. Then you will need to think about how to implement them, how to make them happen in your application. That's where the most interesting part starts. But the good news is that you can uncover very interesting bugs, and also the bugs that might happen in the real world. So if you test for one user and your application supports multi-user and synchronous operations, and you didn't plan for it, I have some bad news for you. You might encounter some bad things when the application goes to production. So the main outcome of state transition tests, the negative ones, is trying to make some inconsistency based on the state transitions. In the worst case, so from the real world here, the example from my experience, in the worst case, I have made an inconsistency in the database based on the user. So I had a user that became unavailable for specific reason I have made happen in the application, and all the admins working with users couldn't do anything about any other user at all. So the admin system made it impossible to add or change new users, or existing ones. Completely all system that worked with changes to user accounts was blocked fully. Very bad thing to happen in production. You don't want it, go and test it. Another way to represent a graph of state transition graph is a graph. So you have states, you have transitions as the arrows here, and this can be also represented as the smaller grid. That's the one listing all possible transitions and the transitions that are not there. And this one shows you the initial state, the action you apply, and the cells give you the destination state. This might be the way to go if you're limited in memory and the focus is on actions, not on states. If the focus is on states, you can go vice versa. This is the initial state, this is the final state, and this is the action you perform to switch from one to the other. These are three possible ways, and depending on your needs, you might want to use some of them, yeah, or one or a few, okay? The applications, when we use which decision trees and state transitions. So obvious use of decision trees is games. I have shown you this example. Recommender systems, when the recommendations are based on previous choices made by the user. Insurance and finance, if it's something based on time. So insurance and finance is mostly cause effect, but if it's based on time, it might be a decision tree when the previous results determine the following results. And as previously mentioned, the reinforcement learning. State transition, yeah, we have already mentioned simultaneous actions, entities and their states. Embedded systems, when you have something in the real world, it is usually described as state transition diagram. So there are some I don't know, buttons to push and to release and so forth. And asynchronous updates. Asynchronous updates, it is also the case where you need to think about state transition. The idea of an asynchronous update is that you can have a lot of updates in a queue, and the updates happen not simultaneously, no, so not when they were triggered, but sometime later. This might be the cause of inconsistencies. You will need to think about state transitions then. Okay, this is about the techniques and how to code it. How to code it? I will be share the presentation and you will be able to click those fancy links. First of all, you can write some code using the libraries for your respective programming language. I have given here Java, Python, and JS. You can Google for more. These libraries are available for, I suppose, almost all modern programming languages. And what you want to Google here. So if this is not the programming language of your choice, what you need to generate your test with these test design techniques. For state transition, you Google graphs. That's the idea. For decision tree, you Google binary trees. Be specific about it, because you don't need the whole graph stuff when you work with a tree. It is much simpler to work with a tree than to apply some generic graph libraries to achieve the same result. So if you want a decision tree, just be specific and go for trees instead of the generic graph libraries. There are also specific testing tools which allow you to use both transition and decision trees. Decision trees also have wider applications when it comes to requirements management and making sure that your requirements are full and consistent. As you have seen on the example before, we might have the leaves that are missing. Your analysis of requirements via some tools applying decision tree might look for missing leaves. That will bring you, might bring you not only the negative tests, but also the missing requirements. So if you want to make sure that your requirements contain all the information you need, you might first run some analyzer using the decision tree on them and see if all the leaves are there, if all the leaves are defined. If some of them are missing, then your requirements might not be full, might not be complete, okay? And based on that, you can also evaluate the consistency of the requirements. Are all the leaves defined differently? So it is not only about missing trees, missing leaves, but also are the leaves different? So are the results different for different paths through the tree? This is the decision tree tools. This one can help you with that. One more thing is that you can build the paths and see them highlighted. You can have a look at this one. The thing is that you need some models, and this is more complicated stuff from requirements perspective. Not many companies use model-based requirements, and there are not many business analysts that apply this approach in practice, so it might not be that widely used. As for the state transition, these tools will give you, so the Altwalker is quite a nice tool. If you use simple graphs, it's very nice tool to have them visualized and to make sure that you test all the paths, or if you base your test on just transitions, that all the tests, all the transitions are tested, it highlights it. It highlights the transitions and makes sure that you do not miss any of them. But if you want to build the negative test, as previously shown on this grid before, then you might go for libraries. For libraries which are used in test design. These are the examples, and these are generic graph libraries. From my personal experience and practice with state transitions, I use the generic graph library, NetworkX. Suppose I give it here. I used this one, and the reason for that was that I needed quite complex operations on graphs. I needed to combine a few graphs into one, then I needed to build a complementary graph to have the negative test, and then I needed to build some paths with the definite lengths through that graph to have the negative tests I wanted. So that's why I went with a generic graph library. But if you want something more common, you might want something simpler than that. And in this case, it is suppose advisable to use the specific test, so the library for testing purposes, for the purpose of creating tests based on exactly this test design technique. These are the simpler cases, okay? That's how to implement it. And finally, answering the question, practical examples, for all the techniques I've mentioned. Are there any questions apart of that? We can come back to the previous stuff if there are any.
No questions in the chat.
Okay. Okay, then let's consider the examples, and I would very much like you to participate a little bit with me. This is the example of okay, this is something that defines if an email is a spam or not a spam, okay? Spam or not spam. And this model is kind of random based. Okay, these final, so you see these kind of rainbowish conditions. These are definite. So these are conditions that result in either true or false. That is okay. The bad news are the last, these final conditions which are either green or red. These are actually not the final leaves. These are the conditions that result in either true or false with the given probability. Okay, that's some kind of reinforcement learning. So we try to add a little bit of randomness to make sure that we are not stuck in some local optimum. That's what reinforcement learning does. There is this little randomness part there, and we can see it in this model. So as soon as this condition is applied, the last one is applied, we have this something making a true-false decision with the probability of 60% for false and 40% for true. Yeah, therefore, you see that is red. So the probability of false is higher than the probability of true. That's also the logic of coloring of these final conditions. Okay. So in fact, you have not 5. Yeah, you have not 5 leaves here, not 5 paths through the 3, but 10. So this is true, false, and these are final leaves. This is true, false, and these are final leaves with these probabilities, and so forth. My question now is the following: which is the worst case for us from kind of test execution perspective? If these are the conditions, yeah, 60 to 40, 10 to 90, 3 to 97, 80 to 40, 45 to 55, and we do need to test all possible options here, true, false in each case. Which condition causes us the most trouble? Which is the worst case? So which is the worst for us? When we will spend the most of time generating the necessary case? So we will retry one and the same path over and over again until we reach the necessary result. Which is the worst thing for us? Which condition is the worst? Where will we spend the most time on test execution? Okay, that's my question. You can write numbers, yeah, 60 to 40, 10 to 90, and so forth, or you can write the number from left to right. I will consider this one as 1, this one as 2, this one as 3, this one is 4, and this one is 5. We want to have all the possible outcomes. So we want true, false here, true, false here, true, false here, true, false here, and true, false here. Which of the conditions gives us the greatest number of tests? Okay, that's the question. Are there any answers there? Close to 50-50. That's actually the best case for us. We need to generate false and true here. And the one close to 50-50 is the best case because it won't take many attempts to generate either of the outcomes, as they are close to throw a coin and seeing the results. 1 and 2, 60 to 40, and 10 to 90. 1 is actually also quite close to 50. So imagine how many times you need to throw a coin to get heads and to get tails. Yeah, not so many. They are 50-50. Yeah, and same here. So here you will need not so many tests to generate the outcome you need, because they are quite close from probability perspective. So the closer they are, the fewer tests you need. So you need both outcomes. Sooner or later, you need both, and you need to retry as long as you get the outcome you need. But the closer to 50-50, the sooner you will get both outcomes in it. For this reason, between 1 and 2, 2 definitely brings us the worst case, but not the worst, from test execution perspective. So here you see false with only 10% probability. It means that only 10 times, approximately, yeah, it's probability, approximately 10 times out every 100 cases, you will get false, but in 9 cases out of 10, you get true. Yes, 3 is the worst case for you, definitely. So if you consider this one, this is the worst case from test execution perspective. Out of 100, approximately 3 are false, and the rest is true. You will need to execute not 2, yeah, not 3, but very likely you will have to repeat it over and over and over and over again until you get that false for this third condition. Okay, why apply the randomness? Why do that? You might want to get the right answer most of the time, but you can never sure that the answer is truly right. And for this reason, the machine learning models, the reinforcement learning models specifically, might apply some randomness just, to try the other outcome and see how it goes. Maybe it'll bring us the valuable knowledge about the environment, and we will apply it to making further decisions. So this third condition, if it makes the outcome false, it might influence our knowledge about these rainbowish things, yeah. IP is not risky. We don't know how it is defined as risky. We don't know how email is defined as valid. So the result here might cause the changes in how we apply this stuff on top. Okay? That's the idea. And that is why you can see some randomness in your testing. Good news is that if you have the probability, you can approximately, you can kind of give an educated guess how many tests you need in order to generate the result. So think the result you need, yeah? Think about it as 100, so 3 out of 100, yeah? So you might want to do at least 98 tests. You might need to do, yeah, at least 98 tests. 97 might be true, and the 98th might finally be false. It will not always be the case because it's essentially random, but the probabilities at least give you the guesstimate, yeah, the approximate idea of how many tests you will actually execute, which is very important to understand if you want to estimate the execution time. It might be complicated stuff. You might have limited devices, limited capacities, and so forth. So if you have the randomness, make sure that you know the probabilities so that you can estimate the execution time. Okay, that was the first example. The second example is the decision making. Okay, based on the previous state, you see the first and the last state. Yeah, it's time-based. The example is out of healthcare industry, and this is the path. Yeah, the path through decision tree. This is the initial state, this is the possible outcome of the decision tree, and we see essentially 1/5 part of the model. So imagine that you have similar trees for every square on the right, for yellow ones dotted, and so you have a decision tree for each one, and they are applied one after the other. Okay, so the outcome of the decision tree 1 results in applying the next decision tree, and which one is applied is determined by where you are finally. Okay, that is the idea. The question, how many tests do we have here, positive ones? So how many paths through the decision tree are there? Note that you need to count here not only the states. Code samples for automated testing techniques, they do the paths for you. You can use the libraries I have given above. You give them a tree and they give you the set of paths. No, I don't give the code samples here, making things more or less simple. So this is kind of more or less introductory stuff into decision trees and state transition. But the libraries that generate tests for you are quite simple. You won't face any significant difficulties with those. You need to understand trees. You need to understand what you get in the result, and you just use the library on your tree and you get the result. The trick is to understand what you get. And that's what we are talking about today. So how many paths through this tree you can see? How many paths there are? Can we state that there are 5 paths? Judging from the number of squares here. Or not? Are there more than that? Fewer than that? Okay, fewer than that is a stupid question, I suppose. But are there more than that? Do we have any answers on the chat?
Not yet.
Not yet. Okay. So the answer is no, we don't have 5 outcomes. The thing is that, as I mentioned previously, the one and the same outcome can be applied to a few paths through the tree. We have considered that and or example, and there were only 2 possible results, 1 or 2, but they were listed a few times in the tree. So we have listed them as many times as we needed, as the number of paths go. Yeah. Oh, thanks a lot. There are indeed 7 paths, but only 5 outcomes. And you can see that the number of paths is equal, in fact, to the number of these arrows here, not the number of the outcomes. Please be aware, the number of outcomes might not be equal to the number of paths. And one and the same outcome can be used for a few paths. If you want to apply some test generation using the libraries I have given above, you will want to make it equal to the number of outcomes. So you, to the number of paths. So you will need to repeat these outcome as many times as there are paths resulting in it. So if you want to code it, if you want to generate paths through this tree, you will first need to make it the binary. Yes, so you use this 2 times for this and for this, and you use these 2 times for this and for this. Thank you for the answer. I don't know, I don't see the names, but thank you guys. It's nice to know that you're still here with me. One of the, so I have one more example as far as I recall. The example that gives you one more graph, and this is now about state transition, not about the decision tree. This is the graph, which is not a graph. Bad news about this graph is that it is not a graph. What does it mean that it is not a graph? You have 2 states and 3 rows that transition from this this state active to this state suspended, and 2 arrows that proceed from suspended to active. It doesn't happen in the graphs. You don't want to have it there. So if you want to apply a test generation on the graph of this kind, yeah, this is the flow through some API, yeah, the calls that submit the states that result in those calls. If you have this kind of thing, you will need to make it a graph. What does it mean to make it a graph? You will need to double or triple a state, so make 2 more or 3 more states, as many states as you need to have the arrows unique, meaning you need a single arrow that goes from state A to state B. You cannot have 3 arrows, 5 arrows. You cannot have more than 1 arrow going from one state to the other. So you will have one state A and state B and the arrow from A to B. It is allowed to have the backwards arrow. So the arrow, the transition is defined by 2 points, the initial and the destination point, yeah, the destination node in a graph. But you are not allowed to have more than 1 transition, the same one, yeah, between the 2 points. So you cannot have A to B and then 1 more A to B. So this is not a graph. That's bad news. Good news that you can make the transformation to make it happen. You will need to have 3 suspended and 2 actives, and then have active to suspended 1 with this arrow, active 2 to suspended 1 with this arrow, active 1 to suspended 2 with this arrow, active 2 to suspended 2 with this arrow, active 1 to suspended 3 with this. So I hope you get the gist of it. You will need to make a graph. In order to make that happen, you will need to make as many states as there are arrows that correspond to duplicate. Okay. As I have already mentioned, we will need 2 active states and 3 suspended states. What's more, where the problem occurs again, which state will we need to have duplicated or triplicated, maybe, or quadrupled? Which state more, except for active being duplicated and suspended being triplicated, will we need to work with, will we need to change? And how many duplicates, triplicates, so how many copies will we need? Where the problem occurs. Note besides that the graph, like you see now on the screen, is the part of requirements. So this is the thing that you might see in the requirements, because it is not a mathematical graph. Yeah, it's not a mathematical construct. It is something that shows you possible states and transitions. Yeah, possible. This is something describing the logic. That's not a mathematical graph. And in order to make it a mathematical graph you can work with, you can apply the tools to generate tests with, you need to make it a graph from mathematical perspective. So my question was, close for more copies. Can we do? Can we go with 2? That's the question to everyone, but maybe to the author of the previous comments. Can we go with 2 only copies? Thanks, Sonia. Can we go with 2? Or do we need to duplicate for each transition? Does it, so is it necessary? Does it make sense to have separate copies? Yeah, from business logic perspective. Yeah, we have the same closed state here and the same closed state here. Six. Which one? So we have tripled this one, we have doubled this one. Which state do we need to have 6 copies of? Or you count the whole number? Yeah, we have doubled arrows actions. We can go with, yes. Can we go with 2? Yes, we can. Can we go with 4? Yes, we can, but it makes things more complicated. So can we make it happen? Yes, we can. We can make as many duplicates as we want, but it will kind of increase our efforts afterwards. We don't want it, actually. So closed state is the lucky one. We have 2 arrows here, 2 arrows here. And now the final thought, final thought on this example. When you make this graph transformation, you don't make it as kind of the full join, yeah, or something. You need to copy the state as many times as the hugest number of input arrows. Okay, so here, why we need 3 copies? Because there are 3 arrows into this state, and there are 2 arrows into this state, and here there are 2 arrows from here and 2 arrows from here, and we need to consider the hugest number, the biggest number out of the 2. 2 and 2, they're equal. Good news, we need only 2 states, 2 copies. And if we had, so 3 and 1, here we will need 3. 2 and 1, here we will need 2. 2 and 2, here, 2 and 1, sorry, here we will need 2. But if we had 3 and 2, for example, 3 copies would still be sufficient. Can we make it more complicated? Yes, we can, but there is no need to. Okay, that's the idea of this thing, and that is the additional transformation you will want to make before applying the libraries and so forth. So good news, there are libraries for that, generating these tests for you. No need to do that on your own. Bad news is that you will need to do this transition manually. So you will need to consider the graph, sorry, not graph, non-graph. First, think about it and then transform it so that you could apply the libraries afterwards. If you're interested, I can make a separate event on state transition and show you a little bit of code with complicated and less complicated stuff. So please let me know. We can go for state transition only next, and then I will show you NetworkX, a few very simple snippets I have applied, and how you can do more complicated things with graph-based libraries. Yeah, the generic ones. And maybe I can showcase Altwalker if anyone's interested. Okay, and the last example, game theory. Yeah, I have promised you game theory. I have spent some time, a little bit, testing games in my tenure as a test engineer. It was not anything like that. It was a quest. But what I want to show here is the complexity of the task at hand. So what we see here, the initial state is the graph, sorry, not the graph, but the position on the board. Yeah, so this is the position on the board. 0 means that no one wins. -1 means that the player that makes the turn loses, and +1 makes the win. So here is the initial state. You can see that there are 3 empty fields here, 3 possible outcomes. X's turn, X can go here, here, or here. And these are 3 possible outcomes. Yeah, 3 possible places where X can go. It can go here, you see, here, and here. That's the outcome, possible outcome. Note that these are still possibilities, yeah? The possible outcomes, the likely outcome is -1. Yeah, now it's 0's turn. And with so X loses here, yeah? Why X loses? Because 0 goes here and X loses. Same here, 0 goes here and X loses. And here, the probable outcome is that no one wins or loses. Yeah, so if 0 makes a wise turn and puts 0 here, then no one loses. Okay, same here. From this position, it is now 0's turn. There are 2 possible outcomes here, 2 possible cases where 0 can go either here or here. And you can see this in this graph. So note that the number of leaves is not binary. So it is not that you have always equal number, yeah, of leaves here. They win or lose earlier than that. So there might be still free spaces on your game field, but the game might be over. Therefore, the number of leaves here is not that easy to count. And note that we have started not from scratch. Just imagine the whole tree. This is just the excerpt, yeah, just the part of it. Imagine the whole tree. And note that it is a very simple game. I'm sure everyone knows it and knows how to play it and not to lose. But imagine the whole complexity of this stuff from scratch. That's what makes the game trees so complicated. Good news, it's the kind of play by turn by turn game. Yeah, the tactics and tactical turns, the strategy you perform, yeah, turn by turn. But not all games are that way. There might be some simultaneous actions. And here the outer world, the environment, is the adversary, if this is a 2-player game, or adversaries, if there are a few of them. And there is also the outer worlds, the so-called AI, and the real game trees are even more complicated than that, but it is typical not to consider all possible conditions, all possible outcomes, whatever, and focus on kind of some small part you test. So you do not build the whole stuff. It is too complicated to manage and too complicated to follow. You usually build small game trees depending on what you test. Okay, that's the example from game theory. I have built the game tree for request and AI. So without the adversaries, the player interacts with a few AI-based characters, and there are a few possible actions the player can perform based on the choices they make kind of in each decision point. That is it. These are all examples I wanted to show you. Please let me know. I can, I suppose, make the state transition event if you're interested in it. As for the decision trees, I don't see a real reason, because decision trees are fancy, nice, and interesting, but as you might have noticed, state transition has, as a test design technique, a much wider application. So decision trees are very interesting, but very peculiar. So there are not many cases when you need a decision tree, indeed needed. And for this reason, it is a nice thing to think of and a nice thing to keep in mind, but state transition cause effect are more popular from practice perspective. And I suppose that's it for today. Thanks for being with me. Thanks for everyone who listened and who answered and asked questions. So I was glad to have you here. Hope you have something to think about, and it was more or less useful, or at least interesting to think about. And that's it. Maybe someone has more questions to ask. Let's give a few minutes.
Yeah, while we are waiting, I would like to thank you, Hanna, for this enlightening presentation and this set of examples. I'm sure listeners and our participants really appreciate it, and I can't see any questions in the chat. I'll also only see thank you messages.
Thank you.
And yes, I left a link for our feedback form. Please share your thoughts with us. You can also suggest further topics as Hanna proposed. You can write your suggestions, and we will plan something new for you.
I will share the presentation. I think you can share it, right?
Yes, for sure.
I will share it right now. So hopefully you can put it somewhere there, and
yes,
it'll be useful.
Yes, we'll put it in our formal letter. So thanks.
Nice. Thank you everyone for listening, and come back to our other events, Intelia's Most Interesting Events. Come back and have a great evening today.
Yeah, have a great evening. Bye.
Bye, everyone.